Hello, Professor. My name is Michael Abraham Listiawan, and I will present the article of review that you have assigned us as an assignment. And the article that I chose that is correlated to the thermodynamics is the ultraviolet mechanoluminescence from strontium aluminate doped with cerium, and also the co-doping of cerium holmium. So, without further ado, let us continue with the presentation. Now, I will want to clarify on the big things here, especially the objective and results of the paper. The objective of the paper is to report the results of luminescent properties for both strontium aluminate doped with cerium and strontium aluminate doped with both cerium and holmium. And then this paper is studying the effects of the co-doping itself and compare it with cerium doping only. So I would say like single doping. Now the results is quite significant. They are seeing a significant increase of luminescent properties, especially the ultraviolet radiation. And then this paper also discuss about the possible models that can explain why does helium increase or are able to increase the luminescence properties. As you can see here in the results that we will discuss with more detailing data. Before we get to the data, I will want to give you a brief background on the needs for ultraviolet mechanical materials to improve luminescence properties such as blindness. First, mechanoluminescence, if you are not aware of it, it is the emission of phosphorus caused by mechanical stimuli. Well, ML was first mentioned in 16th century, around 1650, in one of the research papers. I think it's quite old, like a journal, and then it has been quite widely used, but the usage itself is limited because of the color of the inability to color tune, and also that the materials or the material selection is quite limited. This paper addressed the problem of the tunability of the color or color tunability. The development of UV ultraviolet mechanoluminescence materials is quite necessary, especially with high brightness, because UV luminescence can be coupled with colored phosphors, and then we can solve the color tunability problem. Because usually, if we want to make a specific color of some materials, especially for the mechanolysis properties, we have to differentiate its doping. Thus, it's quite hard to then synthesize it from scratch, rather than if we can match it with colored phosphors, and then we just need to create this one materials of mechanoluminescence. Then it can it can brighten, it can have the color to color luminescence that that you prefer. Okay, the test material of strontium aluminate is chosen because it is widely used in mechanoluminescence. It has been proven that it can it can create luminescence, especially with europium doping. So with the cerium doping, strontium aluminate is able to luminescence to radiate a ultraviolet luminescence. Okay, we will continue with the experimental results. The key takeaways of this experimental results, as I have already mentioned earlier in the results and background, is that the co-doping of holmium in strontium aluminate impacts positively and enhances the luminescence properties of the materials significantly. If you can see here, both in the left hand side and the right hand side, left hand side is the characterization of the materials itself. So before we measure the or we test the mechanoluminescence properties, we need to test its photoluminescence properties. Just to clarify the wavelength that they're operating, that they radiate, that this material radiate. As you can see in the left hand side, the photoluminescence show clearly that the material radiates UV spectrum for the material's luminescent properties. Thus, uh, it is already established that this strontium aluminate doped with cerium or co-doped with holmium and cerium actually has UV spectra radiation. And then the increase reaches eightfold, as you can see in the upper graphic, that the co-doping, even in photoluminescence testing, shows a significant increase compared to the strontium aluminate doped with cerium. As for the mechanoluminescence properties on the right hand side of my slide now, the compressive float shows a linear trend for both strontium aluminate, both dope, co-dope, and single dope. However, its intensity difference gap is very considerable. As you can see, the trend might be the same, linear, but its increase is very significant. The increase in 100 Newton or 50 Newton, as you can see here, the co-dope strontium aluminate increases more than, I think, more than tenfold of the strontium aluminate doped with cerium. Thus, this this experiment shows a very great result, I think. So here's the thermodynamic correlation. We know that it shows great results, but we have to know why. Why does it? Why does it has much intense brightness compared to the single dope of cerium? The thermodynamics approach here is to answer that apparent question. The thermodynamics approach, or the thermoluminescence, is used to identify the model of the trapped depth, as you can see here in the left hand side. So thermoluminescence test is usually we're putting the materials inside isolated environment that we can heat, maybe an oven to 300 degrees in this paper, and then after and then around a heating rate of around 3 degrees or 6 degrees, 3, 6, and 10, the the rate that they are tested, that they have tested in the paper. And then you can see in the left hand side the graph, there are two peaks in the graph. The higher one attributes to the cerium doping, while the lesser, the second one, the around in a temperature of 150 degrees Celsius, it is attributed to holmium doping. From this data, we can use Huygens-Schreiber method to identify the electron traps, and then they can make the model in the right hand side. We can see the conduction band and valence band, and also the trap depth of each cerium and holmium. You can see in this conduction band and valence band is that when strontium co-doped strontium aluminate is irradiated in UV light, you can see here in the 4F, the electrons are firstly excited from the F4F ground level to 5D level. Since the F5D level of cerium is partly in the conduction band, the electrons can escape to the conduction band with the aid of thermal energy or photoexcitation energy. Then the electrons are trapped from the conduction band to oxygen vacancies and migrate from one trap to another with the aid of releasing thermal energy. Because the 5D state of homium that you can see here is very close, right? It's very close to the conduction band of sodium aluminate host. Thus, the homium ions can easily capture these electrons to form shallow traps. This shallow traps is the key. Shallow traps of holmium. When a stress was applied, these trapped electrons can be excited by strain energy because it's shallow. It is easy. We don't need a lot of energy to excite this electron. The electrons can also come back to the 5D level of cerium via oxygen trap and conduction band, which is similar to the equine process. So that's it. That's the main reason why the holmium actually increases the luminescence properties significantly because it forms shallow trap depth. And we can know this only by the Hugenstrand method or the thermodynamics approach that we use. Without this, we may not know why, even though we are able to increase the luminescence. It is very apparent and also critical to know the cause of the increase, because by knowing the cause of the increase, we can continue the improvement. We can continue the improvement by selecting the materials accordingly that is maybe similar to homium or maybe totally different. This approach can determine that. That's why it is important. That is why it is very important in this paper. Thank you.